Hi everybody, my name's Allison Daubert. I'm the teacher in residence for the physics department here at Bridgewater State University, and we're back with another physics problem for you. So we use elevators on a daily basis. We all just use them as part of our lives, but have you ever thought about how they actually work? So an elevator is actually an example of an Atwood machine. So this is a model of an Atwood machine that I have here. And what happens is that in an Atwood machine, you've got two masses that are connected by a cable over a pulley. So what a pulley does is it works to change the direction of the force. And both masses, when you release them, accelerate together. But what's cool is that when you have one mass and another mass that are connected together and their masses are just a little bit different, it causes the acceleration to be nice and constant but less than g, because you wouldn't want to be in an elevator that's free falling. So this is an example of an Atwood machine. So what we're going to do is we would like you guys to solve a real world problem involving an elevator. And so here's our elevator. And you can see that we've called M2 the mass of the elevator where everybody actually stands. So a standard mass for that is around 2,000 kilograms. So I'm going to label that here. And that would be the mass of the car plus the mass of the people in it. This M1 is the counterweight for that. I want you to figure out what that M1 should be if you want your elevator to have a nice acceleration of around 1 meter per second squared. That's the 1 meter per second squared is about the industry standard for an elevator. So we'd like our elevator to accelerate upwards at 1 meter per second squared. We'd like the mass of the elevator, M2, to be about 2,000 kilograms. And I'd also like you to find the tension in these cables, because if you're going to design an elevator, you're going to have to be really careful to make sure that your cables are strong enough to handle these masses. And so this can be a little bit of a tricky problem, and one of our physics teachers is going to help you start off solving this problem.
Hi, my name is Dale Quimby. I'm a sophomore here at BSU, and I'm a physics education double major. I want to be a teacher because I like helping people learn new things, and I have fun being able to help them. So for this problem, because the acceleration for the second mass is going up, and the acceleration for the first mass is going down, and they're accelerating together, you'll want to keep in mind that the reference frame is going to wrap around the pulley. Because they're both going to be accelerating at the same time because of the rope and the pulley moving. So let's draw the force diagrams for both the objects. So for mass 1, there's going to be a force going down because of the force of the Earth on the mass. That's not straight. And there's also going to be a force going up because of the tension from the rope. The force of the tension is going to be smaller than the force of the Earth on the mass. And for the second object, there's going to be the force of the Earth on the mass going down, but is smaller than the first one. And there's also going to be a tension force going up that is equal to the tension force of the first object. So from here, you can use Newton's second law to be able to find the tension of both objects, the tension of the rope and the mass of the first object. And once you find the mass of the first object, you're going to want to evaluate to make sure that the mass is in kilograms, that the tension is in newtons, and that the acceleration is equal to 1 when you plug in both of them into the equation.